Good afternoon, everyone. I'm Daniel Fryer, and I'm here today to talk about our project Recon, which is a system to verify file system consistency at runtime. And this is work that I've been doing in collaboration with my colleagues at the University of Toronto. So, as we all know, file systems store data. And to do so, they also store metadata to manage this data. And this metadata tracks allocation of blocks and organizes files into directories. Unfortunately, while it's in memory, it's vulnerable to corruption by bugs in the file system or elsewhere in the kernel. Metadata integrity is crucial. Even a small corruption of only a few bytes is enough to lose a large quantity of data. What's worse, this can occur silently, propagating to disk, at which point it becomes persistent. By the time the problem is found a while later, it may be impossible to repair. It should be no surprise to this audience by this time that file systems actually do have bugs. Still, I don't know what you guys are all doing, but so this table shows a sample of bugs that cause corruption in the Linux ext3 file system. We've just collected it from a couple bug trackers in the kernel mailing list. But what it shows is that even for a widely deployed, mature, stable file system like ext3, there's still a steady stream of serious corruption bugs being reported. So you might be asking, why can't our existing reliability solutions handle this problem? Essentially, existing approaches assume that file systems are correct, and they work hard to faithfully preserve the output of the file system. For instance, journals give us crash consistency. But if we write a corrupted block to the journal, it's just going to be checkpointed or faithfully replayed when we recover the journal. On the other hand, checksums and redundancy schemes like RAID, they exist to protect against problems that arise below the file system. For instance, buggy disk drivers or faulty hardware. None of these can protect against bugs that originate in the file system itself. When metadata is corrupt, how do we even know that it's happened? Short of our users calling up and saying, "You've lost all my data, I'm going to sue you." The best we can do is run an offline consistency checker like FISCheck. And so these checkers verify properties that are necessary for file system correctness. For instance, in file system 1 here, a consistency property might be that no data block can be referenced by more than one metadata block. If this does happen, then data can be overwritten or perhaps improperly exposed to the wrong user. In another file system, this might not be true. It might be possible for two metadata blocks to share so long as the reference count is accurately maintained. But in any case, these offline checkers check all the consistency properties across the entire file system, looking for any violation. The problem with this is that it's really slow, and it's getting slower as disks are getting larger. It also often requires taking the file system offline for some or all of the check, and this can take hours or even days on a large array. Once the problem, the time it takes really discourages checking on a regular basis. So by the time you actually find a problem, making correct decisions about repair might not even be possible. In the case of an improperly shared block here, we don't even know which file it should be, the block originally belonged to, and it might not matter because it's been overwritten multiple times. So there's, not much we can do about that. So the problem is that metadata can be corrupted by bugs in the file system, and existing techniques are inadequate to protect us against this. So now I'll present Recon, which is our solution, and it's a system for protecting metadata from bugs originating in the file system or elsewhere. The key idea, which I'm about to walk you through, is to check consistency at runtime. Then I'll talk about the design of Recon and how it does this, and we'll look at an evaluation of Recon's ability to protect consistency and its performance. So the key idea of recon is to ensure that every update results in a consistent file system state. To put that another way, if there's a pending metadata update that's going to corrupt the file system, we prevent it from becoming durable. So this avoids the need for file system repair completely, because as far as the stable storage is concerned, the corruption never happened. Of course, the challenge is that these consistency properties that are checked are global. In the previous example of double block allocation, verifying this may require a full scan of all the block pointers to ensure that no two conflict. And we can't possibly run FISCheck at every write because it's so slow. What we can do is transform the global consistency properties of FISCheck into fast local consistency invariants, which we check against only the updates that are being made. And so this lets us make an informal argument, an informally sort of inductive argument for the consistency of the file system. So let's say we start in a consistent state, either a clean new file system. We'll also assume that we're using schemes like block checksumming and RAID to handle errors below the file system. Now at runtime, we'll just check what is changing using these local consistency invariants. And so specifically, we'll do it before the changes actually become persistent, so that we can be sure that the resulting new state of the file system will also be consistent. And this maintains our initial assumption. Let's take a look at the transformation from one of these global consistency properties into a local consistency invariant. ext3, one property in ext3, of course, is that you can't share a block between two metadata blocks. You're not allowed to doubly allocate. And so to enforce this during normal operation, ext3 maintains a block bitmap. And so when it wants to allocate a block, it finds a free bit in the bitmap, and it writes a pointer to the inode. And when both these updates have been made, then allocation is consistent. Now, assuming that these structures were correct before we made this update, then the only thing the enforcement of this consistency property depends on is the correspondence between these two updates. So the associated consistency invariant is this. We see a bit flip in the bitmap from a 0 to a 1 if and only if we see an associated block pointer set to that block. Now this invariant is going to fail if either update's missing. For instance, if we set a bit in the bitmap and don't set a pointer, we've allocated a block, but we have no way of reaching it, and so that block is sort of lost to us. On the other hand, if we set a pointer without flipping the bit, then either we've just doubly allocated or we're setting ourselves up for future double allocation. Either way, this is bad news. So one important question is, can we do this kind of transformation for any consistency property that a file system would need to maintain? So our claim is that file systems need to maintain consistency as they operate, and they need to do so efficiently. And so file systems are structured to maintain consistency in a reasonable manner. So we can take advantage of the structures used to do this in order to write efficient consistency invariants that we can check at update time. So you've seen what we're checking, and what we're checking is the global consistency properties turned into local consistency invariants. But when can we check them? Invariants may involve changes to multiple blocks, and so if we check blocks at arbitrary times, we might end up checking in the middle of an operation, and we shouldn't expect it to be consistent at that point. So our atomicity problem is solved by the transactional model used by many file systems for crash consistency. So it's at the boundaries of these transactions that the file system itself is claiming to be consistent. So at this point, we can actually check our invariants. But it's important that we do the check before the commit block reaches disk, because at that point, the transaction has become durable. So if we want to make sure that it's consistent before it's persistent, this is right when we have to do the check. So that's the key idea behind the runtime consistency checking that Recon does. So let's take a look now at the design of Recon and how it does it. Recon can't depend on buggy file system code or any of the data that this code has touched. And so to isolate itself from the file system, Recon operates below the file system at the block layer. From here, it can intercept all the I/O between the file system and the disk. Now, as the file system sort of writes metadata updates, Recon buffers them in a metadata write cache. And when we see the transaction commit being written, it's at this point that we're going to check the invariance on the contents of that cache. To check invariance, Recon needs to do two things. First, it needs to be able to identify the structures within that updated metadata. This requires interpreting the metadata without depending on the file system. So we need to interpret the metadata ourselves. Second, it needs to compare the structures in the updated metadata with their previous versions to establish exactly what changed. And so these logical changes are what the invariants are all about. So to make this efficient, Recon also keeps a read cache, which it accumulates by reading, whenever metadata blocks are read from the disk. Interpreting the metadata and doing this sort of logical comparison between the old and the new structures is not a file system agnostic operation. So to facilitate this, Recon has an interface through which it can invoke file system specific functionality. For the rest of this talk, I'll be discussing metadata interpretation and the logical change generation process in the ext3 implementation of Recon. So to identify metadata structures, we really need to determine the type of a block whenever it's read or written. So to do this, we can take advantage of the tree-like structure of file system metadata with the superblock forming the root of this tree. As the file system will read parent blocks before it reads child blocks. For example, it'll read an inode before it reads the indirect block that the inode is pointing to. And we see the pointer to the block read before the block itself. And it's this pointer within the parent block that we use to determine the type of the child block. Starting from the super block, say it would read the group descriptor, and from the group descriptor it would read the inode table, and so on. We just sort of follow the pointers. So now that we've identified these different block types, we're almost ready to check invariance. But invariants are expressed in terms of logical changes to structures. For example, flips in the bitmap and pointers being set, as in our invariant here. So Recon identifies these changes based on the block types that it's established through metadata interpretation, and it compares the blocks in the read and the write cache. So we represent the changes, the differences that it finds, sort of at the data structure and field granularity by a set of what we call change records. So a change record has 5 fields, and the first 3 identify what metadata has changed. So the type of the structure, like an inode, the identity, so like which instance of the structure has changed, such as an inode number, and what field within the structure is changing, like a block pointer or the mode or the size. And the other 2 fields give us the change itself, both the old and the new values. So to make this concrete, let's take a look at a transaction and the change records that would result from it and how we would use this to check an invariant. In this transaction, we're appending a new block to inode 12. So we see a few changes. We see a block pointer being set to block 501, and this is the block that we've just allocated to inode 12. We see the size of the inode being updated from 4K to 8K, and we see the sector count going from 8 to 16. At the same time, we're seeing bit 501 in the bitmap being changed from a 0 to a 1, and the number of free blocks tracked in the group descriptor decremented. So let's return to our trusty invariant here. What it's looking for is a match between a bit being set in the bitmap and a pointer being set in a block pointer. And as you can see here, there's no violation in this transaction. Basically, all the invariants can be changed in a manner like this, and if you want more details, you can take a look at the paper. So now that we've shown you how Recon works, let's take a look at how well it works. Many of the bugs in file systems are a result of the inherent complexity of writing a file system. Writing the checking code alone is a lot simpler than writing an entire file system, because we only need to verify the results of the operations. We don't have to actually execute file system operations ourselves with all the concerns about concurrency and fault tolerance and whatever it is that file systems are doing. So additionally, each invariant is sort of being checked independently of the others, and so this further simplifies things and sort of makes the invariants easier to reason about. So in our generic framework, we have about 1,500 lines of code. In our file system specific portion for metadata interpretation, it's another 1,500 lines of code for ext3. And the 31 invariants that we check for ext3 take only 800 lines of code. This is significantly less than an entire file system and all the code that it depends on. To evaluate how well Recon can detect corruption, what we did was inject corruption into metadata as it's being written, and then recorded whether or not Recon detected it. Then we let the corrupt transaction commit and ran E2FISCheck on the corrupt volume and recorded whether or not it caught the same problem. So what the graph shows is the fraction of corruptions caught. The numbers on the bars are the numbers of actual corruption, the absolute numbers. The height of the bar is the fraction of the corruptions caught by either checker. So the wide purple bar shows the corruptions that both E2FISCheck and Recon detected, and so as you can see, there's a substantial overlap. The blue bar on top shows where Recon caught a corruption that FISCheck didn't, but these are corruptions that happened in portions of metadata that were not used at the time, so FISCheck doesn't bother checking them. From the perspective of Recon, they're still interesting because they could represent something wrong happening in memory that we might want to be able to detect. The red bar shows two corruptions that FISCheck caught that Recon didn't, where we missed a check on a flag bit in the inode that isn't currently used in ext3. So basically, we've met our goal of matching FISCheck in terms of the things we can detect in terms of corruption. So one question might be then, how much does it cost? To evaluate Recon's performance, we set up 5 different application workloads to emulate using FileBench. 4 of them were standard FileBench workloads, and one was, which we call MSNFS, was configured to match the sort of the file size distribution from a recent Microsoft study. And what we're showing here is the throughput of these benchmarks, comparing ext3 to Recon. For several cases, the difference is actually within our margin of error. But for the last two, the file server and the MSNFS, there's about an 8% penalty. So most of this is cache misses, either misses in the Recon's metadata cache when it's too small, or misses in the file system buffer cache when Recon's metadata cache is too big, reducing the available size of the buffer cache. But for this set of workloads and configuration of machine, we found that sort of a 128 megabyte cache was a reasonable trade-off. So, in conclusion, we can check all the consistency properties of FISCheck on updates without doing a full disk scan. And this checking can be done entirely outside the file system from the block layer. And the real takeaway is that by preventing corruption from being committed, we completely avoid the need for repair because we haven't overwritten anything. We haven't stomped on any data. We don't need to do any sort of costly repair. This is sort of the advantage of dealing with the problem after the fact. Thank you. I'll take questions now.
Wen Guangwang from Ample. So after you detected the corruption, what happens? Do you stop all incoming IOs?
So we anticipated this question. So in my current implementation, what we do is just halt. We fail stop. We prevent all writes from going to disk so that we don't let a misbehaving file system corrupt anything. So our first priority is preserving what's already on the disk. We've thought of a few different ways we could deal with it. We could try and snapshot the file system and then keep going, and that sort of protects the original snapshot. But going forward, there would have to be some sort of repair to fix whatever was going wrong. The other option might be some sort of micro reboot technique to see if it was a transient failure that we could overcome by retrying the operation. So those are the approaches we've thought of. I don't know if there are other things that could be done.
Ethan Miller, UC Santa Cruz. So I like this stuff. It works very well for ext3. Any idea how you would get it to work, or what kind of issues you might have for a file system that does delayed commits? So I'm thinking of things like Waffle or log-structured file systems where you write out the equivalent of a transaction, but then you write out 100 of them before you write out one block that says, by the way, all these 100 do something.
So that's actually what ext3 does. It's doing group commit. So we see about, so I mean, basically the transaction isn't complete until it's writing the real, the block that makes it durable on crash recovery.
Right, but the thing is that the number of blocks you have to write for ext3 is relatively small. As you said, you write the bitmap out, you write the inode out, and everything else. What I'm saying is that there are group transactions.
We're checking 5,000 to 10,000 blocks at a time here.
Okay.
In a group commit.
Okay. All right, fair enough.
Hey, Keith Smith, NetApp Advanced Technology Group. So I also think this is really cool.
Thanks.
It seems like one way to look at this is you're doing inversion programming. One group of people go and build ext3, and then some smart people from Toronto come and write this checker thing. I'm curious about your experience. I don't see a lot of people going and writing this kind of code for somebody else's file systems. So sort of, if you could give advice to people who are writing future file systems that would make your job easier to write this kind of a checker after the fact, what should people be doing with file systems they're not doing to date?
So in terms of checkable file systems that are easier to check, one thing we've learned from working on Btrfs is that it has a couple properties that actually make it easier to deal with than the next three. One of them is backpointers. If anything, backpointers all the time, everywhere. I love them. It just really means that there's a lot less data for us to have to keep track of on the side. The other thing would be to figure out what your consistency properties are up front and write them in a declarative language like SQL, as the Wisconsin guys did, which we shamelessly ripped off for our invariants.
One thing I was curious about, if you look at a journaling file system, it's going to write the transaction to the log.
Mm-hmm.
Once the disk is acknowledged the log is written correctly, it starts pushing out the metadata. It seems to me that you have to cache those writes and not let them hit the disk if you're going to do this validation. So I'm kind of wondering what happens if you were trying to run a production workload that expects persistence when it does synchronous writes.
So we let the writes go to the journal freely until the commit block. So it's really the commit block that we're at the point of commit is when we stop everything. It'll increase your latency when you're doing a synchronous write, especially if there's cache misses, because it's sort of at that sync point that it has to, before it returns from commit, it's going to have to do all its processing. But the writes themselves have sort of have made it to the journal, but we won't let the commit block go until we're sure that it's good.
But if you set the desync flag or something on your writes, those writes need to take, on the order of a few milliseconds before they're persistent, if the behavior is correct.
So if you're writing synchronously, basically it's just committing every time. So you're writing out a couple blocks, and so you're just paying the cost every time on the sync.
Mm-hmm. That's right. And you don't have any problems with having to wait around for some of the related metadata to get down to disk, because you're not going to see that allocation bitmap come down for quite a while after that transaction needs to be persistent.
So if you're allowing the writes to make it to disk without the bitmap, then you're running in a mode where your file system doesn't have any crash consistency guarantees. So the
replay of the transaction log.
Maybe we can take this offline.
Yeah. Maybe sure. we can figure out what the difference is.
I have a question. Atul Atia, Google. Have you considered applying this mechanism for other things, like for, let's say, distributed systems or
So a couple of things. With distributed systems, we sort of briefly thought about it. The notion of consistency in a distributed system is much more involved, and I know there has been some work elsewhere in sort of enforcing that using invariants sort of between systems. One thing we've thought about is databases or applications that have a file system structure that they want to maintain, and so if they have some sort of transactional model, we could do something similar there, and maybe do something about Outlook mailboxes getting corrupted.
So yeah, Christoph Helvig, Nebula, and I mean one thing I wonder is why you're trying to do that at the block layer. For example, in XFS, and I'm one of the maintainer of that, we basically do a subset of that as a pre-write-out callback inside the file system before we even hit the block layer, which seems much simpler to me.
So it is much simpler. I guess my question would be, at that point, what other than what is in the transaction, what other state are you depending on for the correctness of your checks? And so this was our reason for the block layer isolation, is that we can actually rip this out of the kernel entirely. We can sort of sit outside a hypervisor and still make sure that what's going on is correct, even if we don't trust the operating system, for instance.
Yeah, but that seems pretty weird, because in the end the file system format is not something standardized. I mean, that is something that's totally dependent to what operating system you actually run on it.
Sure, but file system formats don't change quickly. I mean, we certainly, the checking is certainly specific to the file system, but there's some benefit fault model-wise from isolating the two from each other. I think practically, yes, doing this kind of checking before you commit from within the file system is absolutely a good idea for a real system. All right, thank you.
Let's thank the speaker and.